Newton's understanding of gravity was good enough to allow us to fly from the Earth to the moon. But it's kind of got to make you laugh to think that you can go all the way to the moon and back using something that's ultimately just an approximation.
Everything in our universe seems perfect. There are laws governing the entire universe, but certain mysteries have remained unsolved despite decades of research. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These are questions that have fascinated us for millennia. What if I told you that gravity is a lie? It's merely a construct of the human brain. This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. Let's delve into the nature of gravity and why time slows down.
To find out what on earth is wrong with gravity, we need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to address altogether. There's a problem with Newton's theory of gravity, and that's that it just allows us to predict how things move under its influence. It doesn't say anything about why gravity exists or even how it works. It just allows you to calculate things. And Newton knew this, of course. He essentially just said that it's down to God. In fact, he said that the most beautiful system of the sun, the planets and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, I'll give you the tools to calculate how the objects move around, but don't ask me how or why that is. That's down to God.
In the vast universe that surrounds us, there are mysteries waiting to be uncovered. Among these mysteries are the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a strange twist. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for our understanding of how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century, when Einstein proposed two groundbreaking theories, the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments used to explain time dilation is the light clock. Imagine being inside a spaceship moving at an incredible speed, close to the speed of light. Inside this spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel in a straight line, bouncing vertically. However, to an outside observer who is not moving with the spaceship, things look different. They see the spaceship moving at high speed and observe the light beam's path. Since the spaceship is moving, the light beam has to cover more distance to hit the mirror. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a longer diagonal path. Now, here's where it gets interesting. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So in this scenario, time behaves differently depending on your motion. It's not just a concept. Experiments have confirmed these relativistic effects. For example, particles in particle accelerators, like the Large Hadron Collider, can reach speeds close to the speed of light. Scientists must consider the effects of time dilation to make accurate predictions and measurements. The special theory of relativity opens the door to a world where time is not a constant, where it can be stretched and compressed depending on your motion. It challenges our everyday intuition and leads us to the realization that the universe operates in ways far beyond our common experience. Einstein's special theory of relativity, introduced in 1905, reshaped our understanding of the universe's fabric, particularly in terms of time and motion. This theory, in its essence, reveals that the laws of physics apply uniformly for all non-accelerating observers, irrespective of their motion. To understand the special theory of relativity better, let's break down its core concepts. One of the fundamental ideas of the special theory of relativity is that the speed of light is the same for everyone, regardless of their motion. Whether you're standing still or moving at a high speed, light always appears to travel at the same constant speed, approximately 299,792,458 meters per second. This concept goes against our everyday experience, where speeds usually add up when we're in motion. It's as if the universe has a built-in speed limit, and that speed is the speed of light. In special relativity, what we consider simultaneous events may not be simultaneous for everyone. If two events occur at different locations, and you're in motion relative to those events, what you see as happening at the same time may not be simultaneous for someone else at a different vantage point. This seemingly strange idea challenges our conventional notion of time. The concept of time dilation is one of the most fascinating and practical implications of the theory. As mentioned in the first section, time can slow down or dilate, depending on your motion. The faster you move, the slower time appears to pass for you relative to the stationary observer. This effect becomes more pronounced as you approach the speed of light. Imagine two identical twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their Earth-bound sibling. This phenomenon, often referred to as the twin paradox, is a real consequence of time dilation. The reason behind this peculiar behavior lies in the invariance of the speed of light. As the space-traveling twin accelerates to a high speed, the ticking of their clock appears normal to them. However, to an observer on Earth, the space-traveling twin's clock appears to slow down because the space-traveling twin is moving relative to the Earth. Another consequence of special relativity is length contraction. As an object moves at high speeds, its length in the direction of motion appears shorter to the stationary observer. This effect is minuscule at everyday speeds, but becomes more noticeable as an object approaches the speed of light. One of the most famous equations in physics, E equals mc squared, is a direct outcome of special relativity. This equation states that energy and mass are interchangeable. It means that mass can be converted into energy and vice versa. This principle is fundamental in understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. Special relativity isn't just a theoretical concept, it has real-world applications. For example, GPS systems rely on the precise timing of signals from satellites. However, because these satellites are moving relative to us, this time dilation effect comes into play. If the effects of special relativity were not accounted for in the GPS calculations, our navigation systems would be significantly less accurate. The special theory of relativity forces us to reconsider our intuitive notions of time and space. It demonstrates that the universe operates in ways that defy everyday experience. Time is not an absolute concept, but is relative, influenced by motion. The constancy of the speed of light and the relationship between energy and mass are central ideas that have been confirmed by numerous experiments. Now, let's delve into the general theory of relativity, another groundbreaking concept put forward by Albert Einstein in 1915. This theory takes us into the realm of gravity, revealing a profound connection between gravity and the very fabric of the universe. At its core, the general theory of relativity challenges the classical concept of gravity as a force that acts at a distance between masses. Instead, it presents gravity as a consequence of the curvature of space-time. This idea is simpler than it may sound. To understand general relativity, we need to think of the universe as a four-dimensional entity, combining 3 dimensions of space and 1 of time. In this four-dimensional space-time, massive objects such as stars, planets, and even you cause the fabric of space-time to curve around them. This curvature is what we perceive as gravity. Imagine space-time as a vast, flexible fabric. A massive object, like the Earth, creates a dimple in this fabric. When you place a smaller object, like a ball near the Earth, it rolls towards the dimple. This is analogous to what happens when an object falls under the influence of gravity. It's not a mysterious force, it's simply following the curvature of space-time. General relativity provides a powerful explanation for the motion of celestial bodies in our solar system. It correctly predicts the orbits of planets, such as the elliptical path followed by Earth around the Sun. The old idea of gravity as an attractive force didn't fully account for these orbital motions, but the concept of curved space-time does. One of the most striking confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an expedition to observe the bending of starlight by the Sun's gravity. According to the theory, the Sun's massive presence would curve the path of light from distant stars, making them appear slightly out of position during the eclipse. The observations matched Einstein's predictions, solidifying the theory's validity. Just as motion affects time in special relativity, gravity also has an impact on time. In regions of strong gravity, time passes more slowly than in regions of weaker gravity. This means that if you were standing near a massive object like a black hole, your clock would run slower than one located far from such a massive object. General relativity introduces the concept of black holes, which are regions of extreme gravitational curvature. The gravitational pull in a black hole is so strong that nothing, not even light, can escape its grasp. The boundary around a black hole is called the event horizon, and it marks the point of no return. Anything that crosses this boundary is inexorably drawn into the black hole. General relativity also has profound implications for the structure of the universe as a whole. Einstein initially added a cosmological constant to his equations to maintain a static universe. However, when it was discovered that the universe is expanding, he referred to this as his greatest blunder. The theory of an expanding universe, as supported by general relativity, forms the basis for the Big Bang theory, which describes the origin of the cosmos. Another significant prediction of general relativity was the existence of gravitational waves. These are ripples in the fabric of space-time itself, generated by massive accelerating objects, such as merging black holes or neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of gravitational waves, confirming yet another aspect of Einstein's theory. Over the years, numerous experiments and observations have tested general relativity, and it has consistently withstood the scrutiny. Whether it's the precise orbits of planets, the bending of starlight, or the observation of gravitational waves, the theory has repeatedly been confirmed. The statement that gravity is a lie might sound shocking, even heretical, given the well-established nature of gravity in our daily lives. However, in the world of physics, there has always been room for debate, dissent, and the exploration of alternative theories. It's not uncommon for scientists to challenge widely accepted theories. In the case of gravity, there are dissenting voices who question the traditional understanding of this fundamental force. Their arguments revolve around alternative theories, some of which seek to replace or modify our understanding of gravity. One of the most well-known alternative theories is modified Newtonian dynamics, also called MOND. MOND suggests that at low accelerations, gravity behaves differently than predicted by traditional Newtonian gravity. According to MOND, there's no need to invoke dark matter to explain the behavior of galaxies. Instead, MOND proposes that gravity becomes stronger at very low accelerations. A key element of the debate around gravity centers on dark matter and dark energy. These are mysterious concepts that were introduced to explain certain phenomena in the universe, like the rotation of galaxies and their accelerated expansion of the cosmos. Critics of this traditional view of gravity argue that dark matter and dark energy are unnecessary, and that alternative theories can account for the observed effects. Some dissenting scientists argue that Einstein's theory of general relativity is incomplete. They propose that there might be additional, yet undiscovered factors or forces at play that could replace or augment our current understanding of gravity. These scientists explore various possibilities, including theories that introduce new particles or interactions. It's essential to note that alternative theories are not dismissed out of hand. The scientific community rigorously tests these ideas to determine their validity.
In Einstein's theory, where you've got four-dimensional space, then you're prevented from travelling back in time, actually by the speed of light. It fits into the geometry in that way. Though you can imagine wormholes and these ideas that you can tunnel through and take shortcuts. Stephen Hawking has a thing called the chronology protection conjecture. And the conjecture is, from a physics perspective, it seems to make no sense. It's not a way to build a universe to allow you to be able to travel back in time and prevent your parents from meeting before you're born or whatever you do. So there's a conjecture that the laws of nature will always be such that time travel into the past is forbidden. Now that's a conjecture at the moment. It's true in what's called Einstein's special theory of relativity.
Experiments, observations, and calculations are conducted to see if these alternative theories can explain the same phenomena that traditional gravity accounts for. Thus far, while some alternative theories have gained attention, none have convincingly replaced the well-established principles of gravity. It's important to highlight that skepticism and dissent are integral to the scientific method. In the pursuit of knowledge, it's healthy to question established theories and explore alternatives. It's through the skepticism and exploration that science progresses. When scientific consensus is questioned, it can lead to further investigation and a deeper understanding of the universe. Despite the challenges in alternative theories, gravity as described by general relativity remains the dominant and most successful theory. This is because it has consistently passed extensive tests and accurately explains a wide range of phenomena, from planetary orbits to the bending of starlight by massive objects. It's the simplicity and comprehensiveness of general relativity that make it so difficult to supplant. As we've discussed, Einstein's special theory of relativity introduces the concept of time dilation, where time behaves differently depending on your motion. Now let's explore how this theory has real and practical implications, particularly in the context of space travel. Space exploration has always fascinated humanity. We dream of exploring distant planets, stars, and even galaxies. However, there's a fundamental challenge when it comes to traveling vast cosmic distances: the vastness of the universe and the limitations of the speed of light. According to Einstein's theory, the speed of light in a vacuum is the ultimate speed in the universe. Nothing can move faster than the speed of light. This limit poses a significant challenge for interstellar travel, because even with the most advanced technology, reaching the nearest stars would take a very long time. To understand the practical implications of time dilation in space travel, let's revisit the famous twin paradox. Imagine one twin stays on Earth while the other twin embarks on a journey to a distant star at a significant fraction of the speed of light. When the space-traveling twin returns, they would find that less time has passed for them than for their Earth-bound sibling. The space-traveling twin has effectively time-traveled into the future. Time is a precious resource for space travelers. The longer the journey, the more pronounced the time dilation effect becomes. In space travel to nearby stars, where the time dilation effect is substantial, this could mean that astronauts age at a slower rate compared to people on Earth. While this may sound like a science fiction plot, it's a real consequence of the theory of relativity. Consider a future where humanity sends a crewed mission to a nearby star system. Due to the vast distances involved, the journey might take several years or even decades, even at a significant fraction of the speed of light. To the astronauts on board, this journey might feel shorter due to time dilation, but the world they left behind would have aged significantly more. Time dilation doesn't just affect living organisms. It also has implications for technology. For example, computer systems and communication devices on board the spacecraft would need to account for time dilation effects to ensure accuracy and functionality. Space travel at relativistic speeds poses many practical challenges. Astronauts on such journeys would need to consider the effects of prolonged isolation, cosmic radiation exposure, and the psychological impact of being separated from Earth for extended periods. While space travel to distant stars remains a future aspiration, the effects of time dilation are already relevant in our daily lives, thanks to the global positioning system. GPS relies on precise timing of signals from satellites to determine location. These satellites are in motion relative to us and are subject to time dilation. If the relativistic effects were not accounted for in GPS calculations, the accuracy of navigation systems would be significantly compromised. Now let's explore the concept of why time travels in one direction. Time is a concept that governs our lives and the entire universe. It flows in a single, unyielding direction, from the past to the present and onward into the future. This one-way journey of time, from what was to what will be, is a fundamental aspect of our existence. But why does time possess this unidirectional nature? Let's delve into this concept. The key to understanding why time travels in one direction lies in a concept called entropy. Entropy is a measure of the disorder or randomness in a system. It's a fundamental concept in physics and is intimately linked to the arrow of time. In simple terms, entropy tends to increase over time, and this increase in disorder or randomness leads to the one-way flow of time. The relationship between entropy and the direction of time is encapsulated in the second law of thermodynamics. This law states that in any isolated system, the total entropy will always increase, or at best, remain the same. In other words, entropy has a natural tendency to grow, and it never decreases on its own. Entropy is all around us, and its effects are readily observable. For instance, consider a deck of cards perfectly arranged in order. Over time, if we shuffle the cards, they become disordered and random. The initial order had low entropy, while the shuffled deck has higher entropy. The spontaneous transformation from order to disorder is a manifestation of the arrow of time. The arrow of time operates differently at different scales of existence. At the macroscopic level, where we live our daily lives, the increase in entropy is apparent. We observe ice melting into water, or the contents of a stirred cup of coffee mixing and becoming disordered. These macroscopic processes exemplify the one-way flow of time. In contrast, when we look at the microscopic world of atoms and particles, the laws of physics are symmetric with respect to time. This means that at the microscopic level, processes are reversible. If you watch a movie of particles colliding and then run the movie backward, you won't be able to tell the difference. This phenomenon is known as time reversal symmetry. The apparent contradiction between the microscopic world's reversibility and the macroscopic world's irreversibility arises from the concept of initial conditions. The macroscopic world is a result of the sheer number of particles and their complex interactions. The initial conditions in this complex world lead to the emergence of a one-way arrow of time. The concept of time's one-way progression is not just limited to everyday experiences. It extends to cosmic scale. The universe itself exhibits a temporal direction in its evolution. The Big Bang, which marks the beginning of the observable universe, is a prime example of the arrow of time. The universe has been expanding and evolving ever since. At the time of the Big Bang, the universe was in an extraordinarily low entropy state. The universe's expansion has led to an increase in entropy over billions of years, creating galaxies, stars, and galaxies within galaxies. This natural progression of increasing disorder, or entropy, is the reason why the arrow of time in the cosmos points toward the future. The question that arises is why the universe started in such a low entropy state in the first place. The explanation for this asymmetry at the beginning of the universe is still an open question in cosmology and remains a topic of active research. Quantum mechanics, the theory governing the behavior of particles at the microscopic level, plays a role in understanding the arrow of time. It introduces the concept of wave functions, which describe the probabilities of finding particles in various states. These probabilities evolve over time and are typically time-symmetric. However, when we observe the system, we collapse the wave function into a specific state, introducing an element of irreversibility. The arrow of time is not limited to physics and the cosmos. It also extends to our subjective experiences. Our brains process information in a particular sequence, from past memories to the present moment and into the anticipation of the future. This cognitive arrow of time is intimately linked to our perception of the external world's arrow of time. The unidirectional nature of time also raises significant philosophical questions about the nature of reality. It challenges our intuitions and our understanding of causality. We tend to perceive the past as something fixed and the future as open to possibilities. This inherent structure of time shapes our worldview and decision-making processes. The arrow of time is fundamental to our existence. It defines our experiences, the progression of our lives, and our understanding of the universe. Without the arrow of time, our reality would be vastly different. Our actions would have no consequences, and causality would be unrecognizable.